Hello, everybody, and welcome to chapter number 5, which is called Orthographic Views in Multi-View Drawings. We're going to develop a lot of ground knowledge that will be needed for future chapters, and more importantly, will be needed to understand the chapter in question. And I will get more into that. I will get more into that in a little bit. So, as far as the definition, multi-view drawings is what we use in the industry to place three-dimensional objects onto a 2D paper. And we're going to start learning about the standards and the rules that govern these standards in order for us to put those mechanical parts into engineering papers. So something that we need to know, or the first thing that we need to define is the six standard views of any mechanical part. You have the front view, both of the side views, then the rear view, the one in the back, the top view, the one that you have looking from the top, and the bottom view, the one that you have looking from the bottom. So it's just you're moving the set of eyes to where it says. So when you are looking at the front view, it's like you're looking from this point of view, and then the bottom looking from the bottom, looking up from the top. You can place yourself on the top and you can look down, and then in the rear you will place yourself right here, and then whatever your eyes see in the back is what you will be placing on those views. What is important about this is how do we place them into the engineering paper, and what we need to know, because right now it's a little Chinese for you, because like I said, I'm just defining terms. The front view, left side view, right side view, and rear view, they have to be aligned horizontally, whereas the top view, the front view, and the bottom view, they need to be aligned vertically. What is important for you to know is that all these views, they communicate to one another. So the dimension or measurement that you have from here to here will be the same one that you have from here to here. The width that you have from this face to that face is the same one that you have from this face to that face. And the reason why is this is because if you reverse engineer these, you will be able to put it together back to what it was. So this right here, shows you that you can place a 3D object such as this one into a 2D paper just with views. Because when you have things in front of you like normal to your eyes or in front of your eyes, you will be able to see things in real size, and that will help you develop your engineering design, or your design I don't want to say design intent, but your design capabilities as you move forward. Well, a little bit more of what I just said. The top, from, and bottom view, they align vertically, as you can see here, and the other four, they will be aligned horizontally. To draw a view out of place is a serious error. So if you take, for example, the views that I'm showing you right now, and you take the front view and you place it wherever you please, that would be wrong. Because as I told you, they communicate to one another. And I cannot stress this enough. They communicate to one another. And this is very important, because if you're taking an exam and then you place your right side view right on top or something like that, that's completely wrong and it's out of the standard. So you have to know and you have to understand that the configurations of these projections are already set by the standards, and those standards is what governs the engineering industry. So more information and definition. So the three principal dimensions of an object are width, height, and depth. And I'm pretty sure you know that. If you have any part in front of you, the first three things that you can look at is the width, the depth, and the height. And what is important about this is that any principal view will show two of the three dimensions. Sorry, any principal view will show two of the three principal dimensions. Height is shown in the rear, left side, front, and right side. Width is shown in the rear, top, front, and bottom. Depth is shown on the left side, top, right side, and bottom views. Guys, this is all definitions, okay? This is the theory, and you have to be able to have these facts before you get into the chapter. In order to understand the projection method, we have to define a little more, and the first one will be the frontal plane. It's the plane upon which the frontal view is projected. Then we have a horizontal plane, which is the plane upon which the top view is projecting, and profile plane, which is the plane upon which the side view is projected. So when you take a look at this and putting this into a better perspective, we're going to start introducing to something that is called the glass box. A glass box is an imaginary box in which you will be able to place your parts so you can start developing such projections, the ones that we've been defining from the first slide on the presentation. So, as it says, the horizontal plane is the one that is horizontal and in which the top view is projected. Then the frontal plane is the plane in front of your front view, and the profile plane is the one that are on both sides. And this one would show you the profile of the part. If I go back to what I explained you before, this is the glass box unfolded. Okay? Is the same glass box. And this is the method that is widely used in engineering. And while right now it might be a little Chinese to you, I can assure you that as you move in your professional career, you will get used to this like very quickly. Okay? So transferring depth dimensions. So the depth dimensions in the top and side view must correspond. Okay, what this is telling you is what I explained you before. All these three views they communicate to one another. How so? So the dimensions that you have from this face to that face, they communicate onto this one from this face to that face. And whatever you have here between this line and this line will be the same one that you have between this line and that line. Therefore, this view communicates with this as much as this communicate with that one, and then this one communicate with this. And in the book, you will learn that by using a method that is called meter line, you will be able to transfer everything from the top view into the side view. Okay, but up to this point, what is very important is that you realize that the dimensions on the top and the side views must correspond. But not only that, but also anything that communicates between these views. If you wanna maybe have a better idea of what I'm saying, let me just go back and show you that these views communicate with one another. Because, like I said, this is the result of unfolding the glass box. Okay, I'm not gonna get crazy into this particular topic because you're not going to get that far ahead, okay? But when working in engineering, drawing the necessary views is critical. So let's say you're an engineer and you're giving of a mechanical part right in your hand. The engineer will come to you and it'll say, "Hey Chris, you have to draw the following part." When the engineer hands the part to me, I should be able, with my knowledge, to determine how many views I will need in order to fully define this part. Okay? But at the point in which you're right now, which is learning all these orthographic projections, I will always ask you to draw the three principal ones. Which are the three principal ones? Is always top, from, and right side view, just as it is right here. The top, the front view, top view, and right side view. But at some point in your engineering career, you will learn that you can maybe fully define one object only with two views out of the three, and sometimes even one view will be necessary. But I don't want you to get complicated with this. I just included it because it's very important that you know that. So, for example, if you have the mechanical part, the first one that we had, you don't have to draw all six views. Only with three views, you will be able to define your part, okay? And that will be totally up to the designer when you get the enough experience. But usually, up to this point, I will tell you which views you have to draw. Okay, a little bit more information. The front view should show a large surface of the part parallel to the front viewing plane. The front view is the one that shows the shape of the object very clearly, and the front view shows the object in a usual stable operating position. Also, the front view is the one that gives you more details about the part. Okay, so for example, if you have a car and you're drawing the three views of a car, the best front view for the car will be this one because it shows you the profile and the way the cars operates, like not usual because like this one, it doesn't operate that way. Um, if you choose this one, then it's a little hard because you don't get to see all the details and you get to see more details on this one. Okay, that's why they call that poor and not wrong. And that is bringing us very quickly to the first and the third angle projection. And this is very important for you guys, but like I said, this is just definition. So there are two main systems used for projecting and unfolding the views or unfolding the glass box. One is called the third angle projection, which is used in the United States, Canada, and most of South America. And the first angle projection, which is primarily used in Europe and Asia. If you're working in the United States, I can assure you that all you will be using is the third angle projection, and actually this is what we're having in the class. I will not bother, to give you exercises with the first angle, but just with the third angle. What is very important about this, guys, is that you have to at least understand both of them, to a sense that you can explain it to somebody else. So you have the glass box as from the beginning, right? And then you have the quadrants of the angles. You have first one, second one, third one, and fourth one. What you're doing is basically placing the part in each one of these quadrants. So when you have the third angle projection, the part it's inside of the glass box and the plane of projections are in front of each one of the faces. Okay, so if we step in front of this part, then the first thing that we'll see will be the projection plane, and then the part will be behind the projection plane. When it goes to the first angle projection is the opposite. The projection plane goes to the back. Okay? And then because it goes to the back, then you will be able to see things a little different. But the real important thing is that when you have, for example, the third angle projection, the way these planes will be unfold will be from here to here, in this configuration, in a way that your front view will be right here, and this will unfold towards the screen, giving you the right side view, and the top view will fall, towards the screen or towards you, and that will give you the top view. So take these three views and place them right here. It's the way it unfolds. When it goes to the third with the first angle projection, it will unfold. For example, the right side view will go from this 90 degrees towards, the front view. So it'll unfolds like this, you know. So, and when that happens, you have your front view right here and your right side view unfolded to the right side, and then the top view will be unfolded like this, like from here and then 90 degrees going down. And like I said, guys, I would worry to understand the third angle projection first and get very good at it, because then when you get to the to the third angle projection, when you get to the first, then it'll make sense. I can tell you. But the difference between one and the other, and that maybe will be on the exam, who knows, is that, for the third angle projection, the projection plane is in front of you, and then the part is behind the projection plane. On the first angle projection, you have the part and then you have the projection plane. But like I said, I wouldn't worry that much about this. I know that this is not easy at first, and it gets easy. It's easier with the practice, and believe me, we're gonna practice a lot. That brings me to more information. Hidden lines, something very important that you should know. So from this point moving forward, you will be required to draw different type of lines, and the way they come into engineering drawings, they're very important because all these lines have different roles to play onto the paper, and if you understand what they are, then you will be able to put back your part as it's supposed to be. So herein lies an advantage of orthographic views is that each view shows the object all the way through as if it were transparent. So thick dark lines represent visible features, and then dashed lines represent features that would be hidden behind other surfaces. Let me see if I had one right here. So if you see this, for example, the top view, look at the top view, just focus on the top view. As I place the top view, you can see lines that are continuously, those will define the shape of the vase. But then in the inside, we have a circle that goes through that you cannot see if you are right on top of this part looking up, you will not be able to see the holes, but then you have to place the holes as a hidden feature because they're right there. Okay, or if you think on the right side view, look at it, these thick lines will actually show the shape of the object, but then behind the wall you have the cylinder or the hole going through all, and that's why you have those dotted lines. The dotted lines are the ones that are showing the hidden lines. Center lines are the ones that are usually we use them to show an axis of symmetry or of a feature or a part. They indicate also a path of motion and they show the location of circular patterns. The center line is composed of three dashes, one long dash, and another one on both ends of that line. So if you let me just go back to this. So for example, as you can see here, we have a circle, and in order to show a circular surface along with this cylindrical face, we have to place a center line, which is a long line, then a smaller one, and then long line, and the same thing on the other axis of, X and Y. Well, I came back, but this is an example of a central line. You place the center lines all on to show circular features, such as this one, and then also cylindrical ones. So you can see that this one is showing me that this is a circle, but also on the front view, this is the front view, you're also seeing a center line that goes one long, then small, and then another one long. And then you have other examples as well. This one shows the pattern of circles or what we call world circle, but don't worry about that right now. And then the path of motion as well. You have this mechanical part that it should be able to rotate from this point to that point. So when you want to show that ability, then you will place a center line so people can be aware of that. Precedence of lines, something very, very important when you have lines that are on the same place. Let's say, for example, you have a visible line on top of a hidden line. It's very important to know this. So visible lines always take precedence over hidden lines and center lines. If you have a visible line colliding with a hidden line, then the only one that you will be placing will be the visible lines. And if you have hidden lines and center line, then hidden line will take place. So a plane surface. So this is very important just to show you a little bit more information about surfaces. Okay, a plane surface that is perpendicular to a plane of projections appears on an edge as a straight line. If a plane is parallel to the plane of projections, it appears in true size. If a plane is angled to the plane of projection, it doesn't appear in true size. So this is a lot of blah blah blah, and I'm gonna show it to you with pictures. It's much better to see it that way. So if you see a face of an object that is perpendicular to your projection plane, then that will be placed as a line. Just think about it that like in this way. Let's say you are right here on the visible plane. What do you see in front of you? Just take a cube and put it in front of you. That whole plane, you're going to be able to see it just as a straight line because that's all you see. If you place yourself in front of this face, all you see is four lines, right? You cannot see the back. If your plane, the plane that you're defining, it's in front of you, then the four lines will define that plane. So therefore you can see this in true size because you have the things in front of you. And this is a definition that will be carried with you throughout your engineering pathway, whether it's mechanical or electrical or any of them, you will get used to this. When you have the thing in front of you, that's when you can see things in true size. So, for example, this inclined surface, it's inclined when you project the four vertex into the projection plane, you won't be able to see this in true size because it's inclined, right? So if you measure this thing, it will not be the same one as what you see here. It'll be a representation, but not in true size. If an angle is on a normal plane, it will show true size on the plane of projections in which is parallel. If an angle is in an inclined plane, it might be projected either larger or smaller than the true angle, depending on the position. So a straight visible hidden line in a sketch means three possible meanings: an edge between two surfaces, an edge view of a surface, the limiting element of a curved surface. You must examine all views to determine a line meaning. What it's telling you with this, guys, is that when you have a mechanical part and you're interpreting the line, like this one, for example, this is your front view and you have a straight line. If you want to see what this straight line means to you, you have to look at the other views to see exactly what it means. So, for example, I'm going to give you a good example of this. This is the front view, and I see a cube, right? Right here. If I look at this, it looks like a cube, but when I look at the top view, it's a cube that is inclined, X amount of degrees related to this line. Or, for example, another great example of this will be this line right here, the contour. You take a look at the contour and it looks like it's something square, but then when you look at the side view, you will realize that it's actually a cylindrical face, that when you have it in front of you, you see only a straight line. You want to know this? Just take a bottle of water and put it in front of you. What you will see, it will be something square, something similar to the square. And then when you see the profile of the water bottle, you will realize that it was actually a circular profile. This is the best example. You have a singular line, so for you, it should be straight, but then you have to look at the whole picture, which will bring you to the right side view, and then you will be able to see the cylindrical face, which is what represents the contour. So this contour, it's actually represented by this point on top. Okay, so if this doesn't make sense, I'm more than happy to go with you on Zoom, but I hope this make enough sense. And that will bring me to what we have to do in the chapter, which is the locator design. So guys, the whole book will take you step by step, little by little, on how to develop the locator design based on what we have learned. So you will be placing the front view, the right side view, and the top view. And along with this, you will be able to place center line, hidden lines, and things like that. So basically everything that we have just covered. If you didn't fully understand this, I want you to be calm, no problem with that, because this gets, this click together with practice. The more you practice, the better you get at it. And Intro to Engineering will not be the only class that you get to practice this kind of thing. So that's it for chapter number 5. Please stay tuned for more, and I will see you in the next video. Thank you very much.